Hey everybody, it's Dr. Wood, and today we're going to be continuing on our journey in epidemiology and biostatistics. And today I want to talk about a few challenges you might run into in looking at studies and some of the things that the researchers will encounter, and some of the things you want to make note of when you're actually reviewing the literature itself. So I won't bore you with the objectives. You can certainly read these and see how we're going to cover those today. So first off, the big challenge you want to be aware of is something we've kind of alluded to previously, but it's called the multiple comparisons problem, right? We mentioned it back in the intro. We were talking about correlating astrological signs to the reasons why people get admitted to the hospital, and how if you just keep torturing the data and keep testing it over and over and over again, you'll eventually find something statistically significant, even though it might not be really true, right? So let's get into some of the concepts and the ways we'll kind of deal with that. So just to give you an example of the problem with multiple comparisons, let's say you have two samples that are roughly identical to one another, and you make a comparison between the two and you get a p-value back. Now, 95% of the time, it'll tell you that there's no statistically significant difference between the two, but there's always that 5% chance you might find something, right? Well, what happens if you were to run that test a second time? Well, if you did it the second time, you see that you also have that chance, 95% chance it'll show nothing. But now that you combine the two together, you're increasing your chances of actually finding something that you consider to be statistically significant, right? The p-value of less than 0.05. And the problem is you can see that when you start to increase the number of independent variables here, and you can represent this as k, you're going to find that chances are going to go up. So as the number of comparisons you make, the higher k goes when you multiply by 0.95, the higher that chance is you're actually going to be able to find a truly statistically significant difference, right? And so that just means that you can run the same experiment over and over and over again, and you're going to find something eventually, right? It's just that's random chance for you, right? So this is the thing we talked about, type 1 versus type 2 errors. And so in this case here, when you have these multiple comparisons, you're more likely to make a type 1 error where you reject that null hypothesis and say that there is a statistically significant difference between these two. And it's very unlikely to be due to chance alone, when actually it was due to chance, right? It's a false positive sort of result here. And so, again, looking at this graph is just showing you as the number of comparisons goes up, as you keep comparing the data, looking at different variables over and over and over again, the chance you're going to find one or more significant findings goes up pretty significantly here. It's never going to be 100%, but again, eventually you're probably going to find something just by chances alone, right? Kind of like the blind squirrel eventually finding a nut at some point. So one of the ways we can try to deal with this is something called the family-wise error rate. And so basically what it means is when you're, say, doing each of those comparisons and you're giving that 5% significance level, so a p less than 0.05 for each comparison, that's called a per comparison error rate. So if you applied that to each and every time you made a comparison, and you had each individual comparison having that level of significance of 5%, that's when you run into that multiple comparisons problem. And so one of the things that you're going to find is that we can try to correct for this by using something called a family-wise error rate. And again, as I mentioned before, the more you run these random samplings and the more variables you look at and the more ways you try to make those comparisons, the bigger chances you are going to make one of those type 1 errors where you incorrectly reject the null hypothesis when you should not have done so in the first place, right? Because there really is no statistically significant difference between the groups. And so, as I mentioned, when you have multiple comparisons, that significance level has to be redefined, right? And that's when we're getting into that family-wise error rate there. And so, basically, we're saying, well, if I'm going to run, say, 5 different comparisons here, overall, each of them added together should have that level of significance of 5%. And basically you just take the number of comparisons you want to make and then just divide it by that. So that way 5% gets applied to each one of the comparisons in terms of each one having to reach a level of significance of less than 0.01 or 1% at that point. Again, 5 comparisons, each at a significance level of 0.01, add them up together and get 0.05, and you're back here to that original 5% we were talking about. Again, that helps you, it makes it harder to achieve significance because now you have to get less than 0.01 for each of those comparisons, but it's also less likely you're going to make a type 1 error, right? And remember, and it's a general rule of thumb, the more likely you are to make a type 1 error, the less likely you are to make a type 2 error, and vice versa. The less likely to make a type 1 error, the more likely you are to make a type 2 error. It's kind of a delicate balance between those two there. So one of the ways we do this is called the Bonferroni correction, and this allows us to, based on the number of comparisons we want to make, will give us the opportunity to determine what the new p-value is going to be in order to achieve significance as a family-wise error rate. Okay, and this is pretty simple. Basically, based off the number of comparisons you're going to make, in this example here, if an experiment makes 20 comparisons, if you just did that where each one had a comparison-wise error rate of 5%, by the time you make 20 comparisons, you're going to have a 65% chance of finding something significant when, again, the chances of making a type 1 error in that case are going to be pretty high there. What you can do instead is to take that, to determine what the family-wise error rate would be, and take that 0.05 and then divide that by the number of comparisons you're going to make. So 0.05 divided by 20, and now in order for each of those comparisons to show significance, they would have to have a p-value of less than 0.0025. Now again, this is more difficult to find that significance. It's harder to get a p-value that small, but it also means you're less likely to make one of those type 1 errors. Okay. You're more likely to make a type 2 error where you failed to reject the null hypothesis, even though there may be a true difference there, but you just couldn't show it because you could not achieve that very tight sort of p-value. Again, you're making these things more conservative because you'd rather make a type 2 error than you do a type 1 error. So what are some of the traps you can run into when we're making multiple comparisons? One of the big things you can see is what we call data torture, and this is essentially where you're analyzing data without a plan. Typically, researchers need to go into the study having a very clear idea in mind of what sort of comparisons they want to make beforehand, right? So looking at this, you can see that it's a pretty easy trap to fall into, especially when you're really looking to make, define something, right? No one likes to publish negative results, and so this is where that data torture really comes into place here, right? And so basically, here's kind of a funny example of how this might work. Funny if you're really into stats. So imagine, we have a surgeon, a physician who's working with a statistician, and he says, okay, so you've already calculated the p-value. And the surgeon says, yeah, I use this really complicated multinomial logistic regression. And the statistician's like, really? How'd you come up with that p-value? How'd you know to run that particular type of test? And the guy said, well, I was just using SPSS, which is a software suite that runs stats. I just picked a drop-down menu, and you can find the one that gave me the smallest p-value. And I guarantee that sounds ridiculous, but there is probably someone who's run to that exact situation here. Because again, when you're working as a medical provider, very frequently you're not the one running your own stats. Typically, you'll have a biostatistician that you'll confer with, and that will help you out. As an example, for my research that I did on coral snake bites, basically I did all the data collection. I came up with the comparisons that I wanted to make, and then I ran that by a statistician who actually ran the numbers and then came back and showed me what the results were. This is kind of doing it the backwards way, where you're saying, well, I'm just going to keep trying things until I find something that gives me a really small p-value, and then I'm just going to go with that. And obviously, you can kind of tell there's already sort of an inherent sort of problem with that. Okay. And so when you're looking at another example of this, there's a famous mayor, Marion Barry, who is mayor for Washington, D.C., and he said, outside of the killings, Washington has one of the lowest crime rates in the country. Well, yeah, I mean, if you take it out, it kind of leans over the fact that you still have a lot of killings there, right? So just because you can't really whitewash over some of those individual points of data there, it's important to make sure you're having really kind of fair comparisons, as you'll see. So there are a lot of different ways to sort of wring significance out of the data. So for instance, if you were to say change the definition of the outcome, right? So you collect your data, you're not really finding the results you're looking for. And so you say, well, I'm just going to change the goalpost. I'm just going to change what the definition is, right? Or maybe I'm going to try to include or exclude patients based on different criteria. I'll just say, maybe I'll take out a few outliers. They're really skewing the data. I'm going to just cut out a few of these people here. Or perhaps if you're clumping or separating groups differently, this is really important, and this is something I think if you're interested in politics at all, it's something really kind of interesting to look into, is the concept of gerrymandering. This is basically how you can kind of slice and dice different political areas in terms of which people you're counting in each district in order to kind of skew the data to get yourself some favorable political outcomes. I won't delve too deep into that here, but just note that it's kind of one way you can try to change the statistics by using maybe less than honest ways of doing that. And then they can just try different statistical tests, right? So you can just try to keep using different tests until you find something significant. And again, that's a problem with that. most of the time when you're going into medical research or you're doing a study, you want to have your comparisons made out a priori or kind of decided before you even start collecting any of the data. That way you don't just sit there and change the goalpost arbitrarily. You have a very clear plan going forward. And if you don't find anything, well, you just didn't find anything, right? So maybe it's a problem with the study or it wasn't powered sufficiently or whatever the case may be there, okay? And again, as you have any kind of reasonably complicated data set, just based on the number of comparisons there, you're going to find that type 1 error is more likely to occur there, right? And this happens when you can find that if you kind of come into the study and you don't have an idea of what kind of comparisons you want to make, and you kind of just keep making different ones until you find something, that's where you really run into that big problem there. And as I mentioned, editors, when you're writing and submitting to a journal, they'd rather publish papers that actually show positive results than something that said, well, we didn't find anything. And I mean, that's not very exciting, right? So a lot of people, you tend to find what we call publication bias, where you tend to find that a lot of the negative results never actually make it out into the light of day, and you're much likely, more likely to see positive results or something where you actually found a difference there, right? And so it's becoming a big problem here, and I'll show you a video you can check out if you're interested a little bit later on. But as an example, here's a study from 2008, and basically it was an industry-sponsored investigation. One thing I'll always point out to you is to look to see who funded a study. If you're reading a study and it says, wow, blueberries, if you eat a cup of this stuff, you're going to prevent cancer from ever occurring, and it's funded by, like, I don't know, the Blueberry Coalition, you got to kind of ask a few questions like that. But here's an example where an industry-sponsored or drug company-sponsored study was looking at the efficacy of antidepressant drugs. And then looking at the studies that the FDA had access to, they had 74 studies, and it categorized them as either positive, negative, or questionable. And what they found is that of the 38 studies that were positive, 37 of them were published. But then what about the negative or questionable ones? 36 studies there, 22 never got published. 11 were published with kind of a spin that made it look a little better than probably what it really showed, and 3 of the negative study were published with clear negative findings. So of the 74, only 3 actually showed any kind of negative findings. So if you're a medical practitioner, you're reading all these studies here, you might think, well, it looks like antidepressants really work. However, there's a lot of data you're not seeing there, and it may lead you to form a much rosier picture than what's actually appropriate. So here is a YouTube video you can check out. This is Last Week Tonight with John Oliver, where he talks about scientific studies and talks about how media can portray some of the findings of these studies here to some, somewhat ridiculous extremes, as you'll see. It has some adult language, so if you prefer to stay away from that, don't worry. That's fine by me. This is optional viewing. Anywho, so some of the other ways we can see these problems pop up here. So we talk about multiple time points or these kind of sequential analyses. One of the things you have to know is, as I mentioned before, that to properly interpret that p-value, that experimental protocol has to be set up in advance. So you need to know the population you're looking at, the sample size you're shooting for, how you're going to collect the data, and then how you're actually going to analyze the results there. Like I mentioned, it's really tempting to say, I'm going to run these tests. If I don't find anything, well, then I'll try something different. I'll try something different, try to do something different. This is what we call informal sequential testing, and it really should not be used, right? Now, again, if you're just reading a peer-reviewed paper, you may not know the background that went into that, and this is really tough to kind of stamp out here. And again, experiments should not continue when the results are not significant. It needs to stop at that point, right? Because that's what you kind of set up from the very beginning. You can't just keep running it until you find something significant and then cut it off, right? It's really not the way good science should be run. So other ways we can do this, you have multiple subgroups, right? So by looking at, you kind of slicing and dicing the same group of people and looking at them from different standpoints could really lead you to the same errors of multiple comparisons here. So imagine we had a heart disease mock study here. We had 2 randomized groups. They were given the same treatment, and then we identified, say, 6 subgroups, right? So maybe people who'd had heart disease before, or black versus white subjects, or male versus females, whatever kind of subgroups you can think of. And what they found were that the sickest subjects in, say, treatment B group had a statistically significant improvement in survival, so less than 0.025. That sounds pretty good, right? Well, when you keep doing all these different comparisons here, assuming you're using just a comparison-wise error rate, you're going to find that the chance of finding something significant is 26%, right? So even if all the null hypotheses are true and there's really no differences between the subgroups, you still are pretty likely to find something when all said and done. And so by setting these up in advance and by using things like a family-wise error rate, you can use part of that in your analysis to make sure you're kind of more appropriately interpreting the data. So also like disease clusters, right? People will try to find patterns when oftentimes none actually exists there. So imagine you have, say, 5 children in a particular school district and they all developed leukemia in the past year. The question is, is it coincidence? Is it due to a common exposure? And some people might ask the question, well, what's the probability that 5 kids in a particular school would all get leukemia this particular year, right? And you can figure that out based on leukemia rates, right? You could look at pediatric leukemia rates and figure out, well, what's the actual likelihood that in a given school of X many kids that 5 of them are going to end up getting leukemia at that same time. The question really should be, though, is what's the probability that 5 children in any school would develop the same severe disease in the same year, right? Showing that there's some commonality between the 5 there. If it's just 5 random kids that get leukemia, that's not super notable here, but the chances there could be a relationship, that's what we're really looking for, right? And so you have to define things like the population of the schools, is it elementary school, is it high school, the time span you're looking at, and then the severity of the disease itself, right? And you find that thousands of clusters get reported each year, and most of the time they're not really clusters, right? The actual rates are not any higher than what you would normally see from year-to-year basis. And then the other quarter that actually gets investigated are found to be just total coincidences, right? It's just kind of a blip on the radar. And even though that we may think that is abnormal, or we may think that there's something there, when you actually do the testing, it's just a pure coincidence, right? Because chance alone can cause a cluster, right? That's one of those things you have to realize, is that sometimes uncommon occurrences just happen to occur, and you can see these sorts of things pop up. So moving into kind of away from the multiple comparisons questions and getting into whether something's Gaussian or not, right? Remember that when we say something is a Gaussian distribution, that's another way of saying it's normally distributed data, right? And remember, there's a lot of assumptions associated with that. So you're going to find that a lot of the statistical tests we're going to be talking about, especially in the next lecture, are they assume that you're sampling from a Gaussian or normal distribution, and that's not always going to be the case, which is why it's really important to make sure we use the proper statistical test depending on the data, right? And you're going to find that when you're dealing with a normally distributed set of data there, you should have relatively very infrequent, very low negative numbers and very high positive numbers there, right? Because those tend to be outliers. You want these people to sort of balance each other out and cancel each other out and prevent that. So why do we use tests that rely on Gaussian distribution? Well, because we assume that if we're having a random sample, that it should be normally distributed. So that's why we run tests that are geared more towards that Gaussian distribution. The problem you're going to find with these tests that are assuming you have a normally distributed set of data, if your data isn't really actually Gaussian distribution, you're going to find it's more likely to cause a type 1 error to occur, because these are not going to be as conservative as what you're going to see when we have a non-Gaussian distribution or a non-normally distributed set of data. So we're going to look at a figure here that shows a simulated set of data, and each distribution actually shows values randomly chosen from a Gaussian distribution. And you're going to see that unless the samples are very large, you're going to find the distributions tend to look a little less symmetrical, right? So unless you're dealing with hundreds or thousands of points of data, oftentimes it may not look just like that normal bell curve that you would expect to see. And so again, here are different pieces of data looking at body temperature and pulling it out from a normally distributed set of data here. And you can see here that all of these are still normally distributed, even though they don't all necessarily look like the traditional bell curve there, right? And again, our eyes, when we see something that doesn't look like that nice bell-shaped curve, we automatically assume, well, it shouldn't be Gaussian. It's not normally distributed. That's not really a good way to do it. We need to make sure we're using the correct statistical tests to make sure that we can tell, based on the presence of outliers or absence, that this is normally distributed or perhaps it's not. So we have tests that can do that, right? So when I talk about tests for normality, this is something that is testing to see that looking at the data set, looking at the presence or absence of outliers there, what is the chances you get a set of data that is this close to the normal population, or something that's this different from that population there. And so it can basically tell us, and it'll give us a p-value, and we call this a normality test. Now, I'll be very forthright with you. I've failed every normality test I've ever taken. I just can't pass it, as it turns out. Very strange. Seems to be something related to the profession, I think. But what you're going to do is, looking at your set of data there, you got to quantify how far out the set of values differs from the predictions of a Gaussian distribution. So you would basically compare what you think a Gaussian distribution would look like based off your population, compare that with your actual population, and see what the kind of difference is between those. And if it's very, very different, and it's very unlikely you would have a set that is that different from the proposed Gaussian distribution, then it's unlikely to be due to chance alone, and you'd say this is not a normally distributed set of data. Okay. Now, there's a lot of complex tests here, but if you ever see a test from normality, that is specifically what they're looking for. So, and again, they're going to find a p-value here when you do a test for normality. And basically, if the value is high, right, so it's above, say, 0.05, it means that the data set that you have, when compared to that Gaussian population, the difference that you're finding there could be just due to chance alone. It's really not that significantly different, right? Versus when you get a very small p-value, it shows that it's very unlikely that the data set you have would vary this differently from the Gaussian distribution, so it's very unlikely to be due to chance alone, and so it's likely not a truly Gaussian distribution. Okay. So, as I mentioned, with the high p-value here, our null hypothesis when you're testing for normality is to say that there is no difference between my data set and the sample that I'm comparing it to of a Gaussian population there. As I mentioned, if the p-value is large, then the data set is not inconsistent, or it is consistent with a Gaussian distribution. So I don't reject the null hypothesis, and I assume that my data set is following that normal distribution. Okay. So then a normality test can demonstrate that deviation is that differences in my data set is not that different. It's not any more different than you'd expect to see with chance alone. And what you're going to find is with these normality tests that the power of it is going to increase with the sample size, which makes pretty good sense, because the bigger your sample size, the more likely it is very close to the whole population that you're interested in the first place. With a small p-value, it just basically means that we have to reject the null hypothesis and saying that the differences in our data compared to the Gaussian ideal is different enough that it's very unlikely due to chance alone, and then we kind of can't say that our data is normally distributed, and that's going to change what sort of statistical test that we can run on that data set. So what to do when you fail a normality test, right? So basically it's saying that, well, the data that we have is not really matching up, and maybe it's because it's following a non-traditional sort of normal distribution, right? There are a lot of different varieties that are out there. For instance, there's one called a log normal, which I'm not going to get into, but it could be because the distribution is a little different than what you would expect to see. One of the things you can actually do, though, is actually test for outliers, okay? So you're trying to see, like, well, what is it specifically that's causing this p-value to be so small? And very frequently it's going to be due to outliers, people who are testing very high or very low on whatever data you're actually looking at. And if the deviation is pretty small, you may not really need to do much there. But what we're going to see is that for the most part, you need to be switching over to a particular set of statistical tests to make sure that you don't violate any assumptions and you make a type 1 error. This is something we're going to touch on a lot more later on in the class, but basically when you're talking about the types of tests that you're running on a data set, parametric is going to be tests that we're going to be using for normal distributions. So parametric tests are good for Gaussian distributions, and the non-parametric tests are better for non-normal distributions. Okay, these tests tend to be more conservative, and because of that, you're less likely to make a type 1 error. Okay, so just something to kind of think about. When you say that something is more conservative and less likely to make a type 1 error, another way to say that they're more robust, right? They're more difficult to cause you to reject the null hypothesis when you really shouldn't have in the first place. Although remember, the flip side of that is also true. You're more likely to make a type 2 error and not reject the null hypothesis when you really should. So talking about outliers specifically, outliers occur all the time, right? Some of it could be due to errors in how the data was maybe collected, or say you have an invalid data entry. Could be just due to biological diversity, right? Could be just due to you have a patient who is just outside of the normal, right? Random chance, experimental mistakes. Imagine if you were, say, doing certain type of temperature analysis, and everyone was doing, say, oral temperatures, but then someone missed the boat there and decided to do, say, a rectal temperature. That could be an outlier because is collected differently and maybe different than what your other data is going to be looking like. And again, another reason why you may have an outlier is because you have a wrong assumption, right? So something that may look like it is an outlier may not be. It could be just because the distribution is a different distribution, right? Like an example would be a log normal one, where I don't know that I have any slides on it specifically, because again, it's kind of getting into the weeds there. But whereas your normal distribution kind of follows that normal bell-shaped curve, and assume this is kind of normal bell-shaped curve, that's actually pretty good. A log normal would look a little different, where basically it would look more like this. And so because of that long tail on there, it looks like there's a lot of outliers out here, but it's actually just how the distribution works. So not anything to get too in the weeds about, but just something to note there. But again, they can run outlier tests to determine, is it truly an outlier or is it something else? So sometimes identifying them can be pretty difficult, and that's why we need to do tests, right? Because our tendency is if we see something that looks outside of the normal, we just assume it's an outlier, and that tends to bias our results a little bit there. And just to give you an example, here is going to be a few different data sets, and if you just take the high and the low values out of these, it looks like there's a lot of outliers here, right? If you're looking at this data set, let's say this one in particular, everything is pretty well clumped around here, but then you have this one little guy way out at the end here. That would look like an outlier. But if you actually ran the statistical test, you'd find that it actually isn't, right? It's all part of the normal distribution that would be running there. So because of that, we don't want to rely on our eyes or rely on our normal pattern recognition, but rely on the statistics to tell us what it truly is. What are some questions to ask before using an outlier test? Well, it could be things as simple as, was there a mistake in the data entry, right? Someone was trying to type something in and they accidentally typed in 5 instead of 8, right? Easy to do on a keypad. Is it because an outlier really is a code for missing value? Sometimes that can be very specific to how the data is categorized, and sometimes you'll just have a random code that is classified as missing values, and that could be accidentally carried forward and thought to be an outlier. It's a possibility. Was there anything noticed during the experiment, or maybe someone was measuring a temperature incorrectly, or maybe they're measuring a patient's height and they're using with their shoes on versus everyone else measuring height with their shoes off, things like that. And again, consider, is that extreme value just due to biologic diversity? Or is it possible the distribution is not Gaussian, right? So we run these outlier tests. If there truly are outliers, and they're very unlikely to come from a Gaussian distribution, maybe it's just because the distribution is just not Gaussian. So when you have an outlier test, basically, if you can say no to all the previous questions in the last slide there, basically two possibilities actually exist still, right? So you can say, well, the extreme value came from the same distribution as the other value, so at that point you shouldn't treat it really any differently, right? It's just part of the data set. Or if it was because of a mistake, you could either potentially correct that or just remove it. But these kind of things need to be addressed in the data to make sure that you're being fully transparent for that sort of thing there. And again, the test is really just telling us if the values are really sampled from a Gaussian distribution, what's the chance that we'd find a value as far away from the others as this is observed? Obviously, a very small p-value shows that this would be very unlikely to find this value this extreme, whereas a very high p-value would say, well, chances are pretty good that you just find this just naturally just due to chance alone. So if you're having a small p-value, again, you're just going to say, well, I'm going to conclude that the outlier is not from the same distribution as the other values, and you can't say that the data is Gaussian distribution. You have to assume that it's not and switch over to those non-parametric tests, whereas a high p-value says, hey, it looks like this is just due to random chance alone. We can keep assuming our data is Gaussian distribution and kind of move forward with that. As I mentioned, robust statistics just means that it's less likely to make a type 1 error. It just means that it is less sensitive to outliers, right? It means that it is more conservative typically. It's harder to achieve significance when you do this. And so basically you're going to find that ways we do that are to try to analyze the data differently such that outliers are not really going to be affecting us, right? The easiest way to do this is just to use the median instead of the mean. Think back to one of our first lectures we had there where we said that the mean is very sensitive to outliers. You can have someone who scores very high or very low on a particular test, and that can really skew your mean data. But the median is very hard to shift just because of an outlier. We said that the median is less sensitive to outliers, and so because of that, we're going to find that the median tends to be much more robust. So just a few questions here to kind of round things out. Does it make sense to ask whether a particular data set is Gaussian? Not in particular. It's kind of a misconception that you think that when you're running a normality test, it's asking whether your data set's Gaussian. Gaussian is just really referring to a random sampling out of the population there, right? The normality tests are just trying to tell us, is the data that we have consistent with the idea that our sampling came from a Gaussian distribution or not, right? So a little bit of a delineation there. Is it legitimate to remove outliers? Some people see it as kind of like cheating, like you're kind of skewing the numbers a little bit, but it needs to be done with a very clear and consistent manner, and it needs to be reported so that way it's going to be very transparent in the data. Kind of like when we were talking about survival data and we were talking about censoring points of data, that's the kind of thing you need to be transparent about. What does it mean to remove or eliminate an outlier? It basically just means you're not going to be including that value in your analyses there, right? And again, we can run these outlier tests to see, like, is it really an outlier or not? Because more often than not, we're probably going to identify something as an outlier when it probably isn't. And then how should the outlier removal be reported? Usually the papers are going to state, hey, these are the data points that we removed, and here's why. So if there are any questions, please let me know, and I'll talk to you guys soon. Thanks a lot. Bye.